Alright, so this is a review of acids and bases. Key things you need to know are, first of all, basically, the definitions of what bases are, acids and bases are. So there's three definitions of acids we're using chemistry. Arrhenius definition is anything that produces H plus solution, H plus in solution. So that's the simplest definition. Bronsted-Lowry we say is anything that donates an H, and that'll be key to kind of figuring out that later. When you look at it, you have to be able to identify an acid or a base based on whether or not you lose an H or gain an H. And finally, Lewis acids are substances that accept electron pairs. So that's the three types of acids. Three types of bases. Most common one we're familiar with is OH. Anything you put in solution produces OH is classified as a base. According to Bronsted-Lowry, we say a base is anything that accepts H plus ions. So you're a H plus acceptor, according to Bronsted-Lowry. And then finally, bases, Lewis bases, are anything that donates a pair of electrons. In order to donate a pair of electrons, you have to have a lone pair of electrons. So that's an easy way to spot a Lewis base. And in order to be a Lewis acid, you have to be able to have like a positive charge or a space to accept electrons. One of the key things you have to do on the AP exam every year is you have to be able to spot Bronsted-Lowry acids or bases. So if you look right here, the way we do that is we look in before and after. So if you look right here at HF, the side before, you look at it after. You ask yourself, what's the difference between one and the other? It's either going to gain an H or it's going to lose an H. In this case, HF loses an H from left to right, which makes that, according to Bronsted-Lowry, that is an acid. We look at, change the color of the pen here, we look at H2O. H2O from the left and the right, what's the difference? From here to here, it's either going to gain an H or lose an H. Notice how there's two H's here, three H's there, it gains, that would make that a Bronsted-Lowry base, because it gains an H, because it accepts an H plus. Going back the other way, that would be the conjugate acid. This would be the conjugate base, because the reverse reaction, we say it's a conjugate base because it gains an H plus. We look down here at SO4. SO4 2 minus, the difference between here and here. When it goes this direction, if it gains an H, it's a base, and it does, so we say, according to Bronsted-Lowry, that's a base. Here, we look at this one, HCO3, the difference from this side to this side, it loses an H, therefore it is considered a Bronsted-Lowry acid. If it's an acid on this side, it's a conjugate base on the other. This would be the conjugate acid. Key thing you need to know for the AP exam. Another thing they ask is conjugate acid-base pairs. Just remember, to get a conjugate acid, all you have to do is add an H plus. So you take something like NO2 minus 1. You want to know what its conjugate acid is, you basically go HNO2. Conjugate base. You're looking for a conjugate base of something, rip an H off. So for example, HCN, you want to know its conjugate base is, rip the H off the front of it, you have CN minus, that is its conjugate base. So when you look at a conjugate base pairs, the difference is just an H. To get a conjugate acid, you're going to add an H, and to get a conjugate base, you're going to remove an H. Definitions of acids. The strong acid, we say, completely disassociates, which means it breaks up. It's a good breaker-upper. So for example, HCl breaks up 100% into H plus and the ion. That's the definition of a strong acid. Strong acids don't have K values, or their K values are very large. And when we go to calculate pH, we just take the negative log of the value, and that's equal to the pH because it's equal to the H plus concentration. Weak acids, we say, barely break up, partially disassociate. So you produce a little H plus and a little bit of the salt or the conjugate base. Finally, a very weak acid, we say, barely disassociates at all. How do you tell the difference in acid strength? If you look at the Ka values, you look at the weak acids with the largest K value will be the strongest acid. So if you look at these two, 10 to the negative 4, 10 to the negative 4, this number here is larger. Therefore, hydrofluoric acid is the strongest out of all those weak acids. If you look at this one, the next one is nitrous acid, because it's 4.5 times 10 to the negative 4th. So basically, to rank weak acids according to their strength, you look at the Ka values. The larger the Ka value, the stronger the acid. One of the things that comes up on the AP exam a lot is oxoacids. How do you determine the strength? The first thing you look at is number of oxygens. If you take a look at the difference between this acid and this acid, the greater number of oxygens you have, the weaker the bond. It's going to weaken the bond, the easier the H snaps off. So if you look here, this has 1 oxygen, this has 3. Therefore, the break in the bond here, this is easier to break, making that a strong acid. Just like if you compare H2SO4 versus H2SO3. H2SO4, the one with the greater number of oxygens, means it is a stronger acid. So the greater the number of oxygens you have, the stronger the acid. Amphoteric comes up a lot on the AP exam. Amphoteric means that you can behave as either an acid or a base. It means you can take an H or give an H. Typically, most amphoteric substances have to have a negative charge in order to take an H. Water is one of the exceptions. For example, if you look here, water can take an H. It takes an H off NO3, becomes H3O+. So it goes from 2 to 3. Water can also give an H. It goes from H2O to OH-. So the term amphoteric means that you can either give an H or take an H. A great example would be like HCO3-. HCO3-, you can add an H to it because of the negative charge, or you could break this H off and make CO3 2- carbonate. First thing we have to look at when we have to find pH is we have to look, are we dealing with a strong acid, strong base, or a weak acid, or weak base? In this case, HNO3 I know is a strong acid. Now if you're in the multiple choice section of the AP exam, you have to realize that you're not going to have a calculator, but decimal places matter. You can figure out pH based on decimal places. For example, if I had 0.001 molarity of HCl and I need to find out what the pH would be, all I need to do is count decimal places. This says 1, 2, 3 decimal places, therefore the pH of that would be 3. If I had something that was 0.00001 and I need to find out what, and it was molar HCl, I just count the decimal places. 1, 2, 3, 4, 5. pH of the solution would be 5. Because when you take the negative log of it, really, the thing that matters is the number of decimal places. As long as it's a strong acid, same thing goes for NaOH. If I had a concentration of 0.001 molar NaOH, first thing I look at is how many decimal places do I have? 1, 2, 3. So basically, I can figure out my pOH for this based on decimal places. Since it's OH now, would be 3. Therefore, my pH of the solution would be 11. So you can basically use decimal places to figure out pH on the AP exam, at least on the multiple choice part. Last thing that comes up is sometimes you need to figure out what a pKa of something is. Same thing, it's driven by the number of decimal places. If you look right here, this is the Ka value for chlorous acid. Look at the negative exponent. See how it's -2? You can estimate that the pKa is going to be close to 2. You take the negative sign away, and you take the exponent, and notice how the pKa is, in this case, is 1.96. Look at this one right here, hypochlorous acid, 2.9 times 10 to the -8th. If I needed the pKa value for that, and I didn't have a calculator, which you wouldn't have on the multiple choice, what I could do is just take the value of the exponent and kind of ballpark it. If it's to the -8th, I take away the negative sign. The pKa value is going to be really close to 8. And that's how you ballpark numbers on the AP exam. All right.